Welcome to this course on the foundations of continuum mechanics. Today we'll be talking about fluids. Although we have already talked about the constitutive models for fluids, we will go into a bit of a detail today so that we are ready to solve a problem in fluid dynamics. The aim for this week is to be able to demonstrate the ideas that we have learned in this course to solve an actual problem in fluid dynamics. So in this last week, we will put all the ideas we have learned in this course to practice, and this is just a flavor or a peek into what we typically expect in an advanced course on fluid dynamics. So through this short exercise in solving a problem in fluid dynamics using the concepts we have learned in this course, we will be able to appreciate that whatever foundations we have developed in this course are actually useful to solve problems in mechanics. So let's get started. Today's agenda is as follows. We'll start with fluid statics, then we'll move on to fluid dynamics, where we'll talk about the constitutive law that we'll be using along with balance laws to be able to solve a problem later this week. We'll also discuss an important hypothesis that's called the Stokes hypothesis, which helps us reduce the number of viscosity constants to just one that typically we see for quantifying linear isotropic fluids. So let's start with what fluids are. So fluids encompass liquids and gases, and we'll not go into detail of the definition of these phases, but liquids and gases, as opposed to solids, have freedom for their molecules to move around, which differentiates them from the behavior of a typical solid. So a normal fluid, and I'll put normal in quotes here, is not able to sustain any shear stress. So what this means is that if you apply a shear stress to a fluid, the fluid will deform, and it will actually continuously deform. And that is because of the molecular structure of a fluid. The molecules are free to move around in a fluid as compared to solids, where in solids they are tightly bound. So in fluids, if we apply a shearing to some fluid particles, the particles will start moving. That is, they'll start deforming, and this deformation is continuous. And that is the reason, as we have seen in the past and we'll also see today, that we relate the rate of deformation to a shear stress in the constitutive laws for fluids. So when I say not able to sustain a shear stress, what that means is that unlike solids, where if you apply a shear stress, the solid deforms and stays in that deformed configuration under that shear load. But in fluids, the fluid is continuously deforming. But there's an important point here that although the fluids cannot stay stationary, that is, they cannot sustain a shear stress and they continuously deform, but they do resist that deformation. They do provide some resistance to that shear. And this is what separates, for example, different kinds of fluids such as honey and water. So if you take a cup full of honey and try to stir a spoon in that cup full of honey, it's very difficult. So when you're stirring a spoon, you're basically applying continuous shear. So you're trying to generate some rate of deformation, and you have to apply a lot of shear stress to be able to generate that rate of deformation. But if you take a cup full of water, on the other hand, you will see that to generate the same rate of deformation, that is the same kind of velocity gradients in the cup, you will have to apply a lesser shear stress. That is, you have to apply a lesser force. So this is what we meant by the two fluids resisting that shear. Although they are deforming, that is, they are not able to sustain that shear, they continuously deform, but they provide different resistances. That is, for the same rate of deformation, you have to apply different shear stresses in the two fluids. So let's put a star here. So a corollary of this statement above is that if you have a fluid at rest, that means that there is no shear stress acting on any plane in that fluid. So we can say that A implies that for a fluid at rest, there is no shear stress acting on any plane inside the fluid. Because if there was any plane where there was a finite shear stress, then that means the fluid would start deforming continuously for that plane. So by that logic, there is no plane where there is shear stress in a fluid at rest. So this is going to be a starting point for discussion on static fluids. So in general, we study fluid statics first because that's more simpler. And then we move on to fluid dynamics where we study the fluid mechanics of moving fluids. So let's take an arbitrary point P inside a fluid domain. And in fact, what we do is we create a cutting plane like this passing through the point P, and we only analyze part 1 of the body. So remember, this is a configuration that is assumed by a collection of fluid particles. So I'll erase this part because we're only interested in studying part 1 for now. So let's say this is the normal to the plane that we have assumed, and then there's a traction that will be acting on this plane. Let's call this T n hat. Now, since we said that this is a fluid in a static situation, so that means that the traction here has to be along the normal. So that's some constant times n hat, because there is no shear stress on this plane, because there's no shear stress on any plane. We say the reason is because sigma shear is 0. And since from the Cauchy stress formula, we can write this as sigma ij and j equals k n I. So this becomes an eigenvalue problem in the sense that we say sigma ij minus k delta ij times ni is a 0. So this means that this normal that we've taken here in this figure is an eigendirection, and this k that we have taken here is an eigenvalue for this sigma at the point P. So I'll say eigendirection or a principal direction. But we also made a statement for fluids under rest that there is no shear stress on any plane. So by the same logic, if we take any other cutting plane passing through the point P, we will notice that that n hat becomes an eigendirection. So we can write that since there is no sigma s on any plane, that means that all n hats are principal directions. So I'll underline that all n hats are principal directions. And if you recall that if all n hats are principal directions, that means it's a spherical state of stress, and that means that sigma is isotropic. So we can write sigma as this constant K times delta Ej. I'll underline this. Now we also know from the nature of fluid that if you take, let's say, a cuboid made up of fluid particles and you apply a tensile force, then the fluid cannot sustain that. So a fluid can only sustain a compressive force. So what that means is that if you have a normal n hat like this, then the traction has to be opposite to the normal. So from that logic, I can say that sigma ij has to be minus P naught. So P naught is just a number times delta ij. So I'll write the reason. Since fluids cannot sustain a tensile force, or I can say that is they can only sustain a compressive force. And this P naught, which is a positive quantity, is called a hydrostatic pressure, or also known as thermostatic pressure. So if you're dealing with a gas, for example, we can write that this P naught is related to density and temperature theta. So we can write a function like this. So this comes from the equation of state from the idea of thermodynamics. And that is the reason this P naught is also known as thermostatic pressure, because this is related to the temperature theta through the laws of thermodynamics. So if I take the trace of this equation, so we get sigma ii is minus P naught times delta ii, and delta ii we know is 3. So this implies that P naught can be written as minus 1/3 the trace of sigma. And if you recall, that is 1/3 the trace of sigma was called the mean normal stress that was given as sigma m. So as a summary, for fluids under rest, we see this form of our sigma. That is, our sigma is isotropic and compressive in nature. And this P naught, which is called the hydrostatic or the thermostatic pressure, can be found out as the mean normal stress. And by the way, if you're dealing with an ideal gas, then this function f actually becomes P naught is rho r theta. And for real gases, we may have modified relations depending on the nature of the gas. So let's move on to fluid dynamics now. That is, we're talking about moving fluids. So for a static fluid, we showed that sigma is minus P times delta Ej. I'm not adding a P naught here because this pressure will be modified, because now we'll add terms for fluid dynamics. So this isotropic part in sigma basically tells us that there is no shear stress on any plane in the fluid. So to handle fluid dynamics, and we know that motion in a fluid is caused because of shear stresses, so we add a tau ij, which is a term in sigma that is responsible for shear stresses. We'll say this is a part that causes shear stress on different hypothetical cutting planes in the fluid, and this is what basically results in the motion in fluid. And this tau is called the viscous stress tensor. I mean, it's a part of sigma, so it's a part of the stress tensor, but it's a viscous stress tensor because it will have the effect of the fluid viscosity contained in it, as we'll see soon. So if I had to define tau for now, I'll simply say that this is sigma ij minus the isotropic part, which has the pressure effect as we see from this equation. Now, if you compare this tau to the tau that we discussed last week in the fluid constitutive models, there we said that tau is the deviatoric part of sigma. But for the discussion right now, we're not putting that condition yet. We'll let that condition evolve through our arguments. But for now, we are not assuming anything other than that tau is sigma minus the isotropic pressure part. So let's write that there's no condition on tau ij to be deviatoric yet. I'm writing yet because eventually we will see that tau is deviatoric part of sigma, but as of now, that condition is not assumed yet. Now this P that we have here is actually the thermodynamic pressure, because defining pressure from the laws of thermodynamics is the easiest thing to do. So that means that the function that relates pressure, density, and temperature is the same function that we used for static fluids. Although in fluids at rest, we call this thermostatic pressure, but that's coming from the laws of thermodynamics. So as a summary, our sigma is split into two parts. One is an isotropic part, which is minus P, which is the thermodynamic pressure, which is uniquely found out from this equation of state. So we have an isotropic part. There's no confusion as to what the pressure is here. And then we have a part which is basically whatever is left after removing the isotropic part from sigma, and that is called the viscous stress tensor. So this viscous stress tensor tau is responsible for the motion in the fluid. And when the fluid is not moving, that is, we're talking about fluids at rest, then this tau is 0 and we only have minus P times delta Ej. So let's call this B. So I can take the trace of B, or taking the trace in B. So we get a sigma II. So we said I equal to J here is minus P delta II plus tau II. So this simplifies to sigma II is minus 3 times P plus tau II. So I can write minus 3P as sigma II minus tau II. So this implies that P is minus 1/3 of sigma II minus tau II. So what we notice is that unlike fluids at rest, the thermodynamic pressure here is not negative of the mean normal stress sigma. It does have a contribution from tau as well. So we say that thermodynamic pressure P is not the same as in fluids at rest. So let's now talk about constitutive modeling. So we said that this tau is what causes motion. So this has to be some function of dkl, that is our rate of deformation tensor, because in fluids we do not talk about deformation, we talk about the rate of deformation. Because when you apply a shear stress to a fluid, you see that the fluid starts to continuously deform. So it makes sense to use the rate of deformation to quantify motion in fluids. We say that as it's the tau that causes continuous deformation. So if you're talking about a linear fluid, then what that means is that this tau can be written as some kijkl times dkl. And remember this from our discussion last week for linear fluids. So just like we had for linear solids, an element in the tau tensor is a linear combination of the 9 elements in the rate of deformation tensor. That's what this equation means. So this kijkl is a fourth order constitutive tensor, and all the viscous properties of the fluid are contained in this K. And whatever ideas we talked about for linear solids are applicable here as well. So this kijkl has minor symmetries, so we can reduce the number of components, but we'll take a jump here and we'll talk about isotropic fluids. Now, isotropic materials are the materials for which the constitutive properties are not a function of direction. Now, think about it. If you have a fluid and the fluid molecules typically are free to move, then what we notice is that there is no directional preference to the fluid properties. So, most of the fluids are isotropic fluids. Well, right, most fluids are isotropic materials. However, there are exceptions. So except for some suspensions, so we'll say, so for isotropic linear fluids, so we already said that the fluid we're talking about is linear, and then we're also assuming now it's isotropic. We can say that kijkl is isotropic fourth order tensor. So we get this constitutive model that tau ij is some lambda star times delta ij times dkk plus 2 times some other coefficient mu star times dij. Let's box this. And this is the constitutive law for linear isotropic. That basically means Newtonian fluids. And this is exactly what we saw in our discussion last week for constitutive equations for Newtonian fluids. And note that most of the fluids we deal with, like gases, air for example, or water, are Newtonian. So we'll restrict our discussion in this week for applying the ideas of quantum mechanics to fluids for Newtonian fluids. And these two coefficients, lambda star and mu star, are the viscosity coefficients which contain the information about the nature of the fluid material. So let us now write the complete expression for sigma in a Newtonian fluid, that's a linear isotropic fluid. So sigma Ej was written as minus P times delta Ej, where P is the thermodynamic pressure, plus tau Ij. Now tau we just showed that for a Newtonian fluid can be written as lambda star delta Ej times dkk plus twice mu star times dij. So that's the expression or the constitutive law for a linear isotropic fluid relating the stress tensor sigma to the rate of deformation tensor and the pressure dij and p respectively. So if I take a trace of this, that is I set I equal to j in the equation, what I get is sigma ii is minus 3 times p plus 3 times lambda star times dkk plus 2 times mu star times dkk. So since we have terms with dkk here, so we'll combine them. So this becomes minus 3p plus 3 times lambda star plus 2/3 mu star times dkk. So this is sigma ii. Now what we'll do is we will write the expression for minus 1/3 of sigma ii. So basically I divide both sides by 3 and multiply by a -1. So this becomes P, that is the thermodynamic pressure, minus lambda star plus 2/3 mu star times dkk. So let's call this C. Now we'll define something called a mechanical pressure that I call P small m. That's a very mechanical way to do it, where we say that this is simply defined as minus 1/3 of the trace of sigma. So this is a definition. So that's how we define a mechanical pressure. And thermodynamic pressure, that is this quantity here, let's write that again. Which was defined using this equation of state as P rho theta, this function equal to 0. So you see that there are different definitions. One's coming from thermodynamics, the other is simply minus 1/3 the trace of sigma. So equation C becomes the mechanical pressure is the thermodynamic pressure minus lambda star plus 2/3 mu star times dkk. So let's call this D. And now I'll talk about something called the Stokes hypothesis. And this Stokes hypothesis says that the mechanical pressure is equal to the thermodynamic pressure. And this Stokes hypothesis, it holds for most of the fluids we deal with. So I'll say that this is true for most fluids except for situations where we have something called expansion damping. And expansion damping is where you have the damping happening for high frequency sound waves in a shock situation in compressible fluids. So these are very exceptional situations. However, most of the fluids we deal with on a regular basis, this Stokes hypothesis will be true. So from the equation number D, if I put the mechanical pressure Pm equal to P, so that basically means that this term lambda star plus 2/3 mu star times dkk is a 0 whenever this Stokes hypothesis is valid. Now dkk is a trace of the rate of deformation tensor. Now, the rate of deformation will not have a 0 trace all the time because it does have an isotropic part as well. In fact, we know that this dkk is responsible for the volume change in the fluid. Remember, this dkk is simply vk comma k, that is the divergence of velocity. And we showed that divergence of velocity or vk comma k is 0 for isochoric motions, but for situations where the volume is changing, which it can in fluids like gases, then dkk is not 0. So dkk is not identically 0 all the time. So what that means is that this term has to be 0. So I'll say that this vk comma k is not equal to 0 necessarily. So this implies that this has to be 0 as a result. So if lambda star plus 2/3 mu star is a 0 always for the fluids for which Stokes hypothesis is valid, then we can say that I can express my lambda star as minus 2/3 of mu star. So we see that we further reduce the number of viscosity coefficients from 2 to 1 for most fluids. So we are left with just one coefficient. So finally, my viscous stress tensor tau ij becomes, so lambda star gets replaced with a minus 2/3 of mu star delta ij dkk plus 2 times mu star dij. By the way, I forgot to mention that this quantity lambda plus 2 by 3 mu star is actually called the coefficient of bulk viscosity. So this coefficient of bulk viscosity, which is written as kappa star, is a 0 under the Stokes hypothesis. And this tau that we have here, if I check tau I now, this becomes a minus 2/3 mu star times delta I is a 3 times dkk plus 2 mu star dkk, and we see that this is a 0. So therefore, this tau that we have here now as a result is a deviatoric tensor. And this was the reason, if you remember last week when we talked about fluids, we said that we link the deviatoric part of sigma to the rate of deformation tensor. So although in the beginning of the lecture, we did not assume anything about tau being deviatoric, but we found that this viscous stress tensor tau, which is responsible for the motion in a fluid, is actually the deviatoric part of sigma. So let's write tau again. So tau from here, so let's take 2 times mu star common, and I write the dij term first minus 1/3 of delta Ij times dkk. Now, if you look at this term, this is dij minus 1/3 dkk times delta Ij. So this is actually the deviatoric part of the rate of deformation tensor dij, because you've subtracted the mean normal rate of deformation from dij. So if I call this, let's say, beta ij, then effectively our fluid constitutive model for linear isotropic fluids with the Stokes hypothesis being valid can be written as tau ij is 2 times mu star, which is the viscosity coefficient, times beta ij. And that's very easy to remember now. So what is tau? Tau is the deviatoric part of sigma ij, that's the Cauchy stress tensor, and beta is the deviatoric part of the rate of deformation tensor dij. And mu or mu star is our dynamic or shear viscosity coefficient. So when we talk about the viscosity of water or honey or air, it is this dynamic viscosity mu star we are talking about. So with this, we come to an end of today's lecture, where we have finally obtained the constitutive model for a Newtonian fluid for which Stokes' hypothesis is valid. In the next lecture, we will derive the equations of motion. That is, we'll start with balance laws, combine this constitutive model into that, and come up with the popularly known Navier-Stokes equations for fluids. Thank you, and I'll see you next.